All right, welcome back to AP Physics 1, Unit 4. This is linear momentum. And then, so this is going to be our last video for this unit. It's a very short unit. There's a lot to unpack in it. And now in this video, we're going to talk about collisions, right? So in the previous video, when we talked about conservation of momentum, we focused on explosions, okay? Now we're going to look at collisions. Now, this is one of my favorite things really to talk about because in the three sports that are pictured, I actually played all three sports growing up. Perhaps my favorite one is hockey. There's Jamie Benn of the Dallas Stars. And I'm a big Army fan. And the picture in the bottom right, that's the goal line stand from the 2023 game. And, you know, I played baseball. What it meant was I was on the team and, you know, just really doing the scorebook. So let's talk about collisions. So when it comes down to the end, there are two types of collisions. So one thing to remember, the momentum will always be conserved. And so how do we distinguish the collisions? Is we look at the kinetic energy of the system. So for an elastic collision, the kinetic energies will be equal. So the kinetic energy going into the collision will equal the kinetic energy coming out of the collision. But what happens is, because of transfers of energy and so forth, the kinetic energies will be different, right? So if I have two objects, the kinetic energies before will be different than the kinetic energies after in terms of the individual objects. But for the system, the kinetic energies will be equal. Now, the second type of collision is an inelastic collision. And what happens is the total kinetic energy of the system will decrease. So you'll lose energy somewhere, and what happens is due to energy, right? Some of that kinetic energy is going to be transformed through the use of non-conservative forces. Sometimes you'll get a question that says it's perfectly inelastic, okay? And what that means is that the objects will stick together and they'll have the same velocity, okay, at the end. And so there are some shortcut things that you can talk. So with a perfectly inelastic collision, if you have one object not moving at the beginning, right? So you have M1, V1 before equals, and now when they stick together, they're going to be one giant mass moving off at a single velocity, which actually makes the solving very simple because it's just going to be M1 VA1 over M1 plus M2. Okay, sorry, writing down towards the bottom of the slide. Okay, now there are some shortcuts for elastic collisions, and the thing to note is that the sum of the velocities for individual objects, they will equal each other. Okay, so I would highlight that somewhere. That is something that you would have to memorize, and that comes through like essentially a page and a half of solving kinetic energy and momentum questions. Okay. Now, remember, with collisions and for all of our processes, delta P is always going to be, the momentum is always going to be conserved. So the difference now becomes the elastic versus inelastic collisions. Okay. So let's look at an example problem. And there are many ways to solve this. I will show a table method, but you can solve it whatever you want to do, right? You can just, separate your page in the before and after, and then kind of accumulate your before side, accumulate your after side. And so here we have, the marble is being shot at one to the left. It says they make an elastic head-on collision, but we want to make sure that that's going to be true because one of the questions is like, is the collision elastic or inelastic? So we have a smaller marble moving at 0.225, heading towards a larger marble, 0.030, moving to the left at 0.18. And so we have this one moving to the right at 0.225, this one moving to the left at 0.180. And remember, we do have to account for the direction. After the collision, the smaller marble is going to move to the left at 0.315. And assuming that neither marble rotates before or after the collision, and that both marbles are moving on a frictional surface, what is the velocity of the 0.030 kilogram marble after the collision, and then is this collision elastic or inelastic, and then is the velocity of center of mass the same before and after the collision. Okay, so if this was a elastic collision and we knew it was elastic before going into this, we could just use the sum of the velocities. But let's go ahead and calculate this out, right? And so sometimes I like to do a table method. And so we have before, after, right? And we have two objects. So this is the smaller one. This is the larger one. And then this is the total. And so what we're going to do is P equals M times V for each one of these. So for the first one, we're going to do 0.015 times 0.225. And we end up with essentially 3.4 times 10 to the negative 3. Okay. Then we do it for the larger one. So we do 0.030 times 0.180. Negative 0.810. We end up with negative 5.4 times 10 to the negative 3. Okay. Now we know the total momentum is just going to be summing those down. So it's going to be negative 2.0 times 10 to the negative 3. So again, to find the total box, we just add these two. But remember, conservation of momentum tells us that before and after equal each other. All right. And now we know the information for the smaller marble after. So we're going to take that 0.015, multiply it by 0.315, and we get negative 4.7 times 10 to the negative 3. Now, how do we fill in this box, right? Because that's our goal, that we're looking for the larger one. Well, we just simply, M1 V1 plus M2 V2 equals our total. So you do a little algebra, so you get P total equal or minus M1 V1 equals M2 V2. So essentially we subtract them, but in the long run, we're going to add them. And so this is going to be 2.7 times 10 to the negative 3. And so now that becomes the momentum of our larger marble. So P equals MV, V equals P over M. And so 2.7 times 10 to the negative 3 divided by the mass, which is 0.030. And it gives us a velocity of 0.009 meters per second. Okay, so that is going to answer the first question, the velocity of the 0.030 kilogram marble. Now, is the collision elastic or inelastic? So now we would do a kinetic energy analysis, if you want to say. So KE before, KE after. And remember, K, 1/2 mv squared. So you do that for all of them, and you find that you get 8.6 times 10 to the negative 4th for both of them. Okay. And so that holds true, right? It tells us now this is an elastic collision, right? Because our kinetic energies were equal. And then the final thing is we just need to figure out, is the velocity of center of mass the same before and after? Okay. And so we would do the center mass sigma mi vi over sigma m. But here's the thing. Here's your sum, right, for both of them. Okay. You don't necessarily have to figure out what is the center of mass. And I don't think I even calculated it in my notes, because I know that because the momentums are the same, the total, if I do a quick calculation, 0.030 plus 0.05, the velocity of the center mass is going to be 0.044. No, that can't be right. Yeah. Yes, it will be, because one of them, in both cases, one's moving to the left. Yes. So there is the velocity of center mass. Okay. All right, so that's going to wrap up Unit 4 here in AP Physics 1. Now, Unit 5 and 6 will be used to be a single unit back in the old days. So they split it up into 2 separate units. And then we're going to talk about rotation in those two units.